Chapter 7, we are changing our focus from basically fractions to decimals. So chapter 6 is all about fractions. We called them rational numbers, of course, right? But there was fractions, yeah? And then now we're looking at decimals. And so everything in chapter 1 where I said, we're not really working with decimals, I want you to keep them in fractions. Well, now you get to work with decimals. And some of you are like, yay, thank you so much. And maybe you'll like it and maybe you won't. So we'll just have to see, right? So to start with, a little bit of language. The word decimal actually comes from the Latin word meaning 10. And we have place values that we need to make sure that we understand with the decimal system. So make 2 lines before the decimal point and then 6 lines after. And then I'm going to write at an angle so that I can get them all in there. So each of these have place value names. If we start on the far left, this is, of course, the tens place. And this is the units or ones place. Either of those are acceptable descriptions. And it isn't like there's only 6 locations after the decimal, but once you see 6 of them, they just start to sort of repeat their structure along the way. So the first decimal place, or the first place after the decimal, is the tenths place. It has a THS on the end, and that's really important. And then we have the hundredths place. And then we have the thousandths place. Does anybody know what comes next? What is it?
10,000?
Yeah, it's 10 thousandths. There's actually a hyphen between the word 10 and the word thousandths here. What's after 10 thousandths? Yeah, 100 thousandths. And I'm going to run out of space if I don't kind of double mine up. It is a hyphen between them again. What's after 100 thousandths? Yeah, millionths. And we could keep going, right? Then you have 10 millions, and then 100 millionths, and then billionths, and so forth. I don't think it gets any bigger than 10 millionths, maybe, in any of the problems that we're working with. That's just sort of what they've used in there. Occasionally, I'll have people curious when we're looking at this number 1 and 2 example, like where do you start to see people using this language? Well, they're using this language in 3rd, 4th grade, but not necessarily with the decimals, right? You hit the decimals about 5th grade in the current curriculums that are going on out there. I get to tell you a lot because my kids are in 5th grade, so I'm seeing this right now. But that's where you're seeing some of these kinds of questions showing up. So right here we have an example. The decimal point, when we're writing the word out or we're saying the word, turns into the word and. That's actually what happens. So I had a really not so very nice teacher in 2nd grade, and she used to get very angry when you said the word and, when you were talking about whole numbers, like 325, and she'd be like, no, and has another meaning. But she'd never explain what it was, so I was like, okay. Like, it didn't make any sense to me. Well, it does. She was right. She just didn't explain anything any further. The and means the decimal point, okay? So starting with the beginning here, where I have the 3 and the 2, what would I do for the 3 and the 2? The part before the decimal point. What is that word? Yeah, it's 32. There are hyphens between 30 and 2 here. And then we have the word and. 32 and. Now, the catch and the thing that's very difficult for my 5th graders, especially my son, is how to write what comes next. So when we write what comes next, we take this number as though it were all alone by itself and not where it currently is. 4236. So if I gave you the number 4236 all by itself, how would you say that word? Okay, that's exactly what you're going to write down next. Okay, so 4,000. Actually, there's no hyphen on that one. I'm not too particular, but just so you know. 4,200 36. And all of that's good. The last thing that we need to do is to identify the place value that we are in. Where do we land? What is my last non-zero location? So we're in the 10,000ths place. Okay? That's when we write 10,000ths after this. With the THS at the end, of course, right? 10,000ths. And just like we want to be able to take the numerical form and write it out in words, or be able to say it in words properly, right? We don't want to say 32.4236 like we always do, right? If we're really saying it correctly, that's not what it is. We want to be able to go the other direction as well. So when we're given the language form, 536 and 76 thousandths, we want to write the decimal numerical form for it. So again, the word and separates things very nicely as my decimal point, right? So the starting part says 536, so that's 536, and then I have my decimal. And this says 76 at the end. But it's not like this. Why? Right, that 76, or at least the 6 part specifically, needs to be in the thousandths place, and right now it's in the hundredths place. So what do I have to do instead? I put a 0 before my 76. Now you don't hear it when we say the word, right? Nobody said the word 0. I mean, the word 0 is not written anywhere, but it's there by default. And so we have to make sure it's there in our value that we write down as well. Is that right? All right, how many of you, which of you, I should say, has taken contemporary math? Okay. Did any of you take it online? Okay. What I'm going to show you next actually shows up online, and it shows up in our textbook here as well. And I do something different than our textbook does. So I do want you to be aware of that, and there is a reason. So let me first explain it from my perspective, and I'll show you what the textbook does and tell you why I choose to do it the way I do. This is called base 10 expanded form. And so it's the same symbols, or the same sort of lines that I had before. If I want to do 3 lines is what I have written down, a decimal point, and then I want to do 3 more. Instead of writing the words for these, I'm going to write the fractional values that correspond after the decimal point. For example, before the decimal point, this is the hundreds place. So anything in this value actually means that's how many hundreds I have, right? This is the tens place. It means how many tens I have, and this is the ones place. And then if I move beyond that, this is what we said was the tenths place. Well, a tenth written in fractional form is 1/10, 1 over 10. The hundredths is 1 over 100, and the thousandths is 1 over 1,000. Another 0. Okay, is that okay so far? Okay, this is called base 10 expanded form, all right? So when we're working with base 10 expanded form, I prefer that you use the fractions, because I think that when you see 1 over 10, you think tenths. But the reality is that your book chooses to do something different. What it does is, instead of writing it as 1 over 10, it writes it as 10 to the negative 1. And instead of writing it as 1 over 100, it writes it as 10 to the negative 2. And 1 over 1,000 writes it as 10 to the negative 3. And it is mathematically correct. There's nothing wrong with it. I just think that it makes it more abstract, and you're actually losing the whole point of what you're trying to do, which is to identify how things are by their place value in fractional form, especially because we just did this chapter on fractions. So what you're going to see in the back of the book, if you look at this problems that we do next, might not look like what I have written down, and I'm okay with that. So let me do an example with you. I'll show you what I would prefer that you write down. I'll show you what the back of the book will say so that you can see how they compare. Okay? So over here, we have another example of a number form of a decimal, and we're going to write it in base 10 expanded form. So the 1 at the beginning is actually 1/100th, or 1/100. It's 1 times 100. I kind of like putting in the zeros. If you leave them off, I'm not going to, be too bad. It's 0, right? 0 times 10. It's 0 tens. Kind of just holds the place. I have 3 ones, so it's 3 times 1. I have 0 tenths, so it's 1 over 10. And then I have 3 hundredths, so it's 3 times 1 over 100. Okay, is everybody all right with that? I mean, do you see where all the pieces came from? It looks pretty clear. Okay, so if I were checking this in the back of the book, I can show you what they're going to have. They're going to have, they might leave the zeros out as well, but they're going to have 1 times 10 squared plus 0 times 10 to the 1 plus 3 times 10 to the 0 plus 0 times 10 to the negative 1 plus 3 times 10 to the negative 2. And it's right. It is absolutely correct. I just think you lose something in doing that you had before. So it is my preference, and I would like for you to use this notation instead, because it has more context that makes sense when you're working with 5th graders. I mean, right? 5th graders don't know these negative exponents. What in the world are you doing? Right? That's crazy talk. So I think you lose something in the translation, basically. Now, visually, a really nice picture for decimals is the decimal square grid. This is a 10 by 10 grid containing 100 squares. So draw yourself a really large square there on the bottom. And what you're going to do, to the best of your ability, is split it into 10 columns and 10 rows. Good luck. Mine never look good, so I'm just going to warn you in advance. And that would be awesome if there were 10 of them, but there's only 8. So that's totally not awesome now, but there's 10. Yep, just as bad as always. There you go. They should, of course, all be the same size. But there's my 10 by 10 grid. Okay? This grid, of course, doesn't work for, 6 decimal places. How many decimal places do you think this is going to work for? 2. Because there's 100 little boxes, so this is a 100th. Right, I can get as accurate as 1/100th in this particular diagram. So if I'm looking at this number and I'm doing number 4, example number 4, to draw a decimal square grid for the number 24 hundredths, okay? So I have the advantage of copy-paste. If you want to just make yourself a note, refer to page 1, you could do that and use your grid. And then it says 24 hundredths. So how much of this do you suppose I'm going to shade in? 24 boxes. And while it's technically correct that you could shade in any 24, if you jump around and shade in random 24s, you're going to make me very grumpy. Okay? Please don't do that. Shade them in rows so that I can count them fast and easy. All right? So this whole row is 10, right? And that whole row makes 20, and then I need 4 more. So that would be a 24 hundredths decimal grid representation. Okay, any questions on that? All right, Theorem 7.1, which comes next, is a really nice connector between what we did in Chapter 6 and what we're doing in Chapter 7. Because it goes back and it talks about what happens with rational numbers and how we think about decimals in terms of them. So if we have a rational number a over b, and it's in simplest form, this is really important. Highlight, underline, star, bold, and do something to draw your attention to the phrase, or to that phrase right there. Super, super important. Simplest form. It can then be written as a terminating decimal if and only if the denominator, when it's factored, has only 2s, 5s, or both. So if the denominator has anything else besides 2s and 5s in it, like a 3 or a 7, right? Right? It could have a 6, but the problem is 6 becomes 2 times 3, and the 3 is the problem, right? So it's not so much that it's anything that is bigger than a 2 or 5, right? Because, you know, the number 10 is okay, because 10 is 2 times 5. But the number 15 wouldn't be, because 15 is 5 times 3. So anytime you have the denominator giving you factors that are not 2s or 5s, then it will not terminate. So we're going to look at some examples, and this part that I highlighted here about it being in simplest form is where we have to start. So just like back in chapter 6, you never left your answer in a form that was not simplified. Here, you're never going to start the problem when you're determining this in a form that's not simplified. So when we do example A, 9 over 24, the first thing you have to decide is it in simplest form? Michaela says no. Michaela, what do you think they both divide by? Yeah, they do. So we're going to divide them both by 3. So what's 9 divided by 3? 3. And what's 24 divided by 3? 8. Are they in simplest form now? Yes, they are. And then I would take the number 8 and I'll factor it. And you can factor it in whatever form you like. Factor trees is one option. If you do factor tree, it would look like 4 times 2. 2 times 2. So what 8 is 8 is actually 2 times 2 times 2. Does that factorization contain anything other than 2s and or 5s? Nope. And because of that, because it's only 2s, or even if it had 5s in it, that would be okay, but 2s or 5s, it means it terminates. So what this is telling us that this is a terminating decimal. But think with me, if we had failed to look at this division at the beginning and simplified, and I did the same thing with the number 24, right? I factored it. The number 24 would factor into 2 times 2 times 2 times 3, right? And if that's all I looked at, it would look like this doesn't terminate because there's a 3 in the factor of the denominator. But the reality is it simplifies and it eliminates itself, right, when I simplify it. So we absolutely have to simplify first. Now, the directions say if it terminates, we're going to find the terminating decimal. So how do you find a terminating decimal? Well, you divide, and you can divide the reduced one or you can divide the original one. Which one's going to be easier to divide? The reduced one, so that's the one we're going to always go with. But if you happen to do the other one, you're going to be okay. Now, I am fully aware that your calculator is fully capable of dividing this for you. But I didn't sign your calculator up for this class, nor did you, right? So I want to see you actually write them down. Because in 5th grade, that's what they have to do, right? My kids don't get to use calculators. They think it's cheating still, and we know it's not. But they still aren't allowed to yet. So you have to be able to show your work to me so that I know that you're going to be able to explain it to the kid later. That's the idea. So obviously 8 doesn't go into 3, but we put a decimal point and a 0, and then we pretend, basically, like the number's 30. How many times does 8 go into 30? 3 times. So there's a decimal point. The decimal comes straight up from the 0, right? And this goes in 3 times. So how many? What is 3 times 8? 24. Fantastic. And when I subtract, I get 6. And since it's not 0, I mean, it didn't end, right? I add another 0, and I bring it down. Now I have 60. How many times does 8 go into 60? 7. 8 times 7 is 56. And if I subtract, I get 4. And then I bring the 0 down again, right? How many times will 8 go into 40? 5. And 8 times 5 is 40, and once they subtract with nothing, then this tells me that I stop. And it will always work if it terminates. Maybe it doesn't work in 3 steps, right? It may be more than that or less than that. But it will always get to a 0 remainder at the end if it's a terminating decimal, which we verified that it should be based on that theorem on the previous slide. So this answer of what does this decimal look like is 0.375. You can put the 0 at the beginning or not put the 0 in the beginning. I don't care, but that's what you'd have. Okay, any questions on that one? Okay, same instructions for part B. What will we do first? Okay, divide them both by 2. You got it. So we'll divide by 2 on top and bottom. So what will that become? 5/12. Then what do? We factor the 12, right? How will the 12th factor? Awesome. So it's 4 and 3. The 4 is 2 and 2. So this factors into 2 times 2 times 3. What does that mean? Right. What part of that's the problem? The 3. That 3 in here tells me that it does not terminate. And the cool thing is if it doesn't terminate, you're done. So that's your preference because there's fewer steps, right? Less work to do. Now, so what happens if it doesn't terminate? Well, we'll talk more about that in 7.3. It's definitely the whole topic in 7.3 to discuss further. But for now, that's where we stop. Comparing values of decimals. I feel like this is everything my children have been doing in the last 3 weeks at school or something. Comparing values of decimals. All right, so when we are comparing or ordering decimals, there are multiple ways of doing it. This one is very nice. On this method, it actually tells you to line up the numbers by place value. So when I say line them up, I like to see them personally. It's easiest for me to just put them stacked sort of like one on top of each other. Then read them from left to right to find the first place where they're different. Compare the different digits. Smaller digit, smaller number, larger digit, larger number. So when we're given a problem, they're usually not stacked up vertically. They're usually written horizontally. So the first thing that I recommend doing is stacking them. So you can use one of them where it is, but I've got the 13, and then I've got 4,919 10,000ths. The next one is 13, and then 492 thousandths. So I just stacked it on top. And then I have 13, 49,183 10,000ths. 4, 9. Okay, my numbers are too small. This isn't working. What's next? 183. And then I have 13 and 49,199. Did I get it all? 100 thousandths. Okay. So these are our four values that we are comparing. And I'm going to highlight as we go to sort of mentally check off, not mentally, but physically check off that we've checked the place values and they match. So for instance, the tens place matches on all of them. So that doesn't give us any useful information for ordering. So does the units place, the tenths place, and the hundredths place. They all match. So the first time that they don't match is in the thousandths place. One of them has a 2 and the rest of them are a 1. What does that tell you? Yeah, it tells you that this one right here is the largest, right? The one that ends in the 2 is the largest. And for all intents and purposes, I can sort of ignore it now, right? It doesn't matter. I know where it comes in line. If I'm ordering these from smallest to greatest, and that's 1 to 4, then it's number 4 in line. So now I'm only considering the next place value. So I've eliminated this one, and now I'm only looking at this one. There's a 9, an 8, and a 9. So what does that tell you? The one that's got the 8 in it is the smallest. So it's going to be the first one in my list when I'm writing them out. So again, I'm sort of ignoring that line now. And I've already eliminated these two as being contenders for anything because I know where they go. But there's something sort of weird happening now. Do you see what it is? Kind of looks like there's nothing to compare. There's only one number left, right? But there really isn't. There's an understood 0 here, and we can write zeros to our heart's content after decimal values, right? They don't matter in the sense of giving me more information, but in sense of comparing, they can be very helpful. So I'm actually now comparing the 0 on the top with the 9 on the bottom. And so what can you tell me now? The 9 is the what? Ariel?
I'm trying to think if it's the next.
Second largest. That's right, Danielle. This is the second largest, which makes the 0 the second smallest, if you want to think about it that way. So I'm supposed to be writing them in order from smallest to largest, and the smallest was the third one listed, which was the 13. 49183. Did I get them in there right? Okay. You can put a comma if you want. That's fine. I'm going to put a less than symbol just to be real clear that I'm putting them in order from smallest to largest. The second smallest, which is the first one in the list, was the 13 with the decimal point, and then 4919. Then the second largest was the 13 and the 49199. And the largest was the 13 and 492 thousandths. So commas between are fine. Less than symbols are fine. Either of those will work. It's also probably worth noting that it doesn't have to be asked to give it to smallest to largest. It could say largest to smallest, and you just flip this list around, and that'd be okay too. All right. Have you heard the word tithe before? I would expect you probably have. If you've stepped foot in a church for any length of time, at some point it comes up in somebody's, words. What is the meaning of the word tithe? It's a tenth. Yeah, the tithe is actually a very specific phrase. It means 1/10. It does not mean what I put in the offering plate. If somebody says something like, I give a tithe of 5%, you can automatically tell them that they obviously don't know what the word means. You can give a gift of 5%, that's great, but that's not tithe. A tithe has a very specific meaning. It means 1/10 of something. So for evangelical Christians, we consider it 1/10 of our increase, so our income. But even in a Jewish tradition, they would 1/10 other things too. Like there's a passage that talks about taking 1/10 of all the spices. Can you imagine going home and measuring out 1/10 of all the spices in your mom's spice cabinet or your spice cabinet? I can't. That sounds crazy, right? I mean, like that's not part of our culture. But it is something that they did further back. So this actually means, in terms of decimals, right? It says, how is this related to decimals? Well, it's related to the decimal 0.1 because that is 1/10, right? And in practice today, we take, I had said this before, but I'll write it out, 1/10 of our income. and we give it. So when my daughter, her name is Abby, babysits, and makes $40, she gives how much as a tithe? Yeah, she gives $4 as a tithe. We have 10 whole minutes to do group work. Are you super excited? I am. I hope you are. All right, so we got group work partners last time, and we will have this. So 7.1 will be due on Monday, homework and group work, okay?